directed graphs. So I've made some changes since assignment one. First of all, the graph will no longer be an adjacency matrix. Instead, will be a adjacency list. I've done this for several reasons, right? One would be that for myself, functions provided below were easy to understand with a list implementation. Also, they were more readily available resources online and advice and tips on how to implement the following functions that were required from us. I did look up for adjacency matrix, and they were harder to implement, and there was probably one or two resources, right? So that's why I've changed my assignment to list. Now, I've also considered that an adjacency matrix does have a larger space consumption, and being that our graph will most likely be sparse, it is much more appropriate to have a list, because if I go here, right, a list has a space complexity of big of E, which is just the amount of edges, versus a matrix, which is big of vertices squared, which is much larger than big of E, where it's just iterating over edges. It could be argued that a matrix does have a better time complexity, as it's constant time, big O of 1, versus a list, which is big O of V. But considering the trade-off between the time complexity and the space complexity, it is more appropriate to go for a list. Hi, this is the shortest path function, an implementation of the directed graph algorithms, assignment 2. Basically, it was an implementation inspired from Geeks for Geeks. They've got an example of Dijkstra's path algorithm, and they use the set, which can be found in STL banana. I also watched this YouTube video. Basically, it's titled C++ data structures, and they basically help you out in terms of implementing a code-based solution to that algorithm. So first off, I've set infinity to a large number. Infinity just represents a very large number. Here I've got 999 million. I've got two vector arrays, neighbors vertices. Then I've got a set named extract set. Now this is going to be used to extract all shortest paths. So we've also got a vector distance, vector preview. Now distance is set to infinity because vertices are unknown. They have an unknown edge cost from the source. That has to be set because it's unknown, and then we'll figure it out after that. So I'm going to keep continuing. We set the distance to 0. Insert the source itself in set and initialize this to 0. Sorry. Do a while loop. You and set the temp to the top vertex in the set. You remove it from the set. Set temp vertex to vertex ID. We get the name of the current vertex. And then we do a for loop. Initialize some variables such as the vertex ID, the neighbor edge cost. Then do an if statement. The current distance is smaller than the total. And if it does not equal infinity, extract new arrays and update the distance. Vector array, update distance. Set new distance, set previous of shortest neighbor to current. Add to set. Trace our way back from target to source by using the previous vector that I initialized up there. And while previous is not equal to 0, I've used another function as a utility function to basically go through this one here that I had to fill in. I won't talk too much about this one. But yeah, basically it's an implementation of Tajin's algorithm. Yeah.